ladies and gentlemen, thank you very much for a nice introduction and for inviting me to be a participant of the program organized by Poznan University. Then dobry, greetings to everybody. I can see in the list of listeners, people, of course, from Poland, Czech Republic, and also some distant spots like Australia and New Zealand. So I am very happy to be in touch with you. So the title of the lecture can be seen. It's not necessary to repeat it. So let us start with a non-separable Banach space, possibly a non-separable metric space. And then, for warming up, I will mention some simple statements how to separably reduce properties of Banach spaces. So, first, X is Hilbert if and only if every two-dimensional subspace is Hilbert. How to prove it? Just to recall the well-known property of Hilbert spaces called parallelogram law. It deals with two elements. So if I have two-dimensional space, then everything is enough. So this is very simple. And the next one is similar to first, but it is not so trivial. The property of being isomorphic to a Hilbert space. So again, it is enough to check what happens with every separable subspace, linear, of course. And how to prove this? Again, parallelogram law plus, and this is a bit tricky and elegant, plus the limits over an ultra filter made from subset of script S X, which is symbol for the family of all separable subspaces. So the limits over ultra filters, actually, they go back to Stefan Banach, but nowadays we prefer this modern approach through ultra filters. So you can check if you like at home later. Next property, reflexivity. Again, reflexivity can be checked just considering all separable subspaces. How to prove this? The only part is simple, and the if part is, by my opinion, non-trivial, but it comes immediately from Eberlein-Shmulian theorem. If somebody can produce a more elementary argument, tell me. And what about Radon-Nikodym property? So this one is also separable, reducible. The definition of Radon-Nikodym property is that if you have any vector measure, x-valued vector measure with finite variation, then such a measure has a Buchner integrable derivative, or we can check it using just Lipschitz mappings from unit interval into X. And if every such mapping has point of differentiability, then it is equivalent with Radon-Nikodym. And because the image of the interval under F is a separable set, then immediately we have the separable reduction. One more property is the property of Asplund, famous, my favorite one, introduced by Edgar Asplund. under different name in the 60s. And later I will speak about it. So, or maybe I should say the definition that every convex continuous function on X has points of fresh differentiability. So a lot of material can be found in Phelps's book, lecture notes from Springer. Remark, excuse me, instead of considering all amount of separable subspaces, it is enough to consider only y's which belong to the so-called cofinal family script C of Cx. And cofinality means that give me any separable space Z, then I can find Y from script C which contains Z. This is a theoretical concept, cofinality. Probably everybody knows it. Now, one warning. Not all properties of Banach spaces are separably reducible. One of them, which comes to my mind immediately, is weakly compactly generated spaces. This one is not separably reducible because, as everybody knows, every separable Banach space is automatically WCG. So if WCG were separably reducible, then it would mean that every Banach space is WCG. And we do have examples of bad Banach spaces which are not WCG, in particular little L1, little L infinity, and many other. Right? Excuse me. Now, so far we consider separable reducibility for the properties of Banach spaces, but in variational analysis in particular, we try and need to separably reduce properties of functions. So let me start with simple examples of this. So now I can go beyond Banach spaces. So X is any metric space. And let F be any function. So any means that may be not even measurable. Any function. And then a simple separable reduction of continuity looks like this. If I have a point X, then there exists a very specific separable Y, which is enough for checking the continuity of whole F. So proof is almost trivial. Yet we can go on, and the next statement is less trivial, and so look, advanced separable reduction. Given a function f and x, then there exists a cofinal in rich family script A, such that for every y from script A and for every x from y, the continuity of f at x can be checked just using the checking continuity of the restriction of f to y. So I think everybody can see the difference between simple SR and advanced SR. Here we have to work with all possible x's from capital Y. And here there appeared a new adjective, rich, new concept. So here is the definition. The concept of rich family goes back to Jonathan Borwein and Warren Morse. Hello, Warren. He is joining us. A family R of separable subspecies of X is called rich if it has two properties. Cofinality, I already mentioned, this one, And the second property, sigma closeness. If I have an increasing sequence of elements of A, and I perform the closure of it, then the result does belong again to A. So this is the definition. We will mention a meet in the rest of my lecture. And now the proof of this advanced separable reduction. So you know the main point is to guess a suitable candidate, a suitable definition of this enigmatic script A. And I think for me, it is not immediate and it needs a bit of time to devise that. Say, I am not saying that this is the only possible definition, but this one work. A consists of all separable y's such that diameter of, this is called, I think, oscillation of F around X of radius A restricted to Y is equal to the oscillation of the whole F. Yeah. And so this is a candidate. And then, of course, we must show first that A is non-empty, that it is even cofinal and even rich. But this is rather a routine thing. The main point is just to guess the definition of suitable candidate. And that's it. You know, such a statement is of not very interest, but just for illustration. And now something extremely important, one property of rich families. If you have two rich families, then the intersection is not only non-empty, not only cofinal, but even rich. Actually, we can take countably many of them. And this is phenomenon which has some analogies. For instance, if you have two sets of full measure, Lebesgue measure, then the intersectional is non-empty and even of full measure. Or if you have two sets of which are G delta dense, then the intersection is again G delta dense. So such a phenomenon. And I very recommend you to perform this homework. And once you do it, then you become sympathetic lovers of rich families forever. At least this was happened to me. And once I spoke with a colleague of mine, Ludek Zalicek, why rich families? And he answered, well, they make a mathematician's life easier. They help to organize things in an easier way. And like here, it may happen that there are two functions, F and G. I find a rich family corresponding to F, and a colleague of mine found another family R prime corresponding to G. And this colleague is a distance spot. And then we can put these two families, perform intersection, and we are done. So wonderful. Now, something more complicated. So continuity is not of much interest, but differentiability is, please believe me. So here I put together separable reduction for differentiability, and you can see a longer cortege of authors: David Price, Ludek Zalicek, Marek Cud, recently me, and other people. So F is any function, not necessarily continuous, not necessarily measurable. And then we can construct a very specific rich family, so that this rich family separably reduces the fresh differentiability. So F is fresh, differentiable, if and only if the restriction is fresh differentiable. What about sub? This means sub differentiability, and for non-experts here is something like a definition. If you take definition of fresh differentiability, it consists of two inequalities, upper and lower. So if you take just lower, then you have sub-differentiability. Similarly, you can have super differentiability. I will not bother you by any more details. Just a comment. First, such a statement for convex functions is due to David Gregory from Australia. In Phelps's book, you can find such a proof. And this time it was not so elegant like it can be done now. And it should be noted that when going from convex functions to non-convex functions, then you have to exert extra non-negligible work. So convex functions are rather simple to check. Warning. Separable reduction is not almighty. There are properties of functions which cannot be separably reduced because of this counterexample. Consider a non-separable little L1, then everybody knows that the canonical norm is nowhere Gatto differentiable. But on the other side, every separable space, in every separable subspace, convex function has many points of Gatto differentiability. This is an old result of Mazur. So this is such a counterexample. And the idea why the separable reduction is not possible for little L1 or gamma is that pressure differentiability is sort of uniform strengthening of Gatto differentiability. And because of this uniformity, we can perform separable reduction. But Gatto differentiability means give me any direction, I can find one tangent line touching the graph of the function. And for another direction, you have different tangent line where the speed of going the ratio to limit are different. So this is the point. Fine. Now, something what I like a lot, such a definition. If I have a Banach space X, then X cross X star is a product, and I consider such rectangles V cross Y. Rectangle means this. V and Y. Yeah, such products. And everybody can see that this blue object is a rich family in whole script Sx cross X star. Now, something less trivial. We can use rich families to characterize Asplund spaces. So there exist, say, 50 different equivalent conditions for Asplund property. Let me recall the most popular one, that every separable subspace of Z has separable dual. So you can take it as a definition, but this is not the original one. And second is there exists a very specific family, let me call it script A, consisting of rectangles, such that for every rectangle we have the following. This canonical assignment of going to restrictions is surjective, that is onto, and moreover isometric. You know, if you take some random v cross y, there are no chances to believe, to expect surjectivity, nor the isometric property. So in order to choose those very specific rectangles, it needs a lot of work and many years. And one more equivalent characterization is that the dual X star admits a projection skeleton, blah, blah, blah. Please be patient. Within 5 minutes, I will introduce this wonderful concept due to Vyacheslav Kubis from our institute, 2009. So just a statement now. And few words about the proof. So implication 1 implies 2 profits from a long bow of ideas across half a century. And here I try to list a cortege of many celebrated authors. Probably, I apologize, I forgot to mention some other, but at least some important stars in this effort. Yeah, many people. David Yost, for instance, is among them. Marek Cud, a colleague of mine from Charles University, and so on and so on. And implication 2 implies 3 is rather easy because, you know, for skeletons, you need some index set, and the index set will be just the Asplund family provided by ordering inclusion. So this, and 3 implies 1 is also quite easy. I wrote some notes, some 3 lines, so this is very easy. So this is what I have to say. If you ask me, please tell me what is Asplund space, then I would refer him or her to the second property. This is sort of skeleton, or how to say, inside the space X. Yeah, so this is very deep characterization. Now, I will present the definition of projection skeleton, but before it, let me recall the famous, notoriously known concept of Joran Lindenstrauss from '65. Here is the definition. I think that maybe everybody from the audience is familiar with this concept. Yeah, and this PRI proved to be a very efficient tool to manipulate non-separable Banach spaces. And for non-experts, just this is something like a very weak analog of the concept of Schauder bases, something like that. So this is a well-known definition. And now the new definition, for instance, WCG are such. The new definition, as I already mentioned, is projection skeleton. And there are some differences. So here you have a lot of projections. Here you have a lot of projections. But these projections, those were indexed by ordinal numbers, those not. They are indexed by some enigmatic, partially ordered, up-directed, and sigma complete set. Gamma. And the properties are: every PS has separable range. This is not the case in PRI. Second, we have this union without closure even. And third is commutativity for those indices which are comparable, not for all. If this were true for all PS, then we would speak about commutative PS. Fine. And the last property is if you have an increasing sequence S1, S2, blah, 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 then you have this. And of course, now you need here the bar, the closure. Now, what we can say about projection skeletons? X admits a one projection skeleton. One means that the norm of every PS is 1. Let me check if I follow the schedule. Yeah, I do. So it, sorry, X admits a PRI. Second, there exists a linear injection from X into C0 bounded, of course. X admits a Markushevich basis. This was not clear immediately, so later Kalenda proved this from Charles University. And some people must be very happy, those in particular who are sympathetic with Markushevich basis. Yeah, so this, I will not recall the definition in this moment. And one more property, there exists a equivalent renorming of the space X, so that the norm is locally uniformly rotant. And this can be obtained. So Vyacheslav Kubis claims this in his seminal paper, this one, but he spends just 2-3 lines with the proof. So more details can be performed modulo Stanin Trojansky's celebrated technology and Václav Zizler's theorems. So this is not immediate. Now, what is the comparison between PRI and projection skeletons? No analogous statements for PRI exist. The point is that on one side, PRI is wonderful concept. So discovered by, introduced by Joram Lindenstrauss. So still is of big importance, but there exists very strange Banach spaces which do have PRI and have no reasonable properties like those. But PRI is still very important, useful, versatile for performing dirty work. Sorry to say that. So still very important. Fact, if the density of X is just the smallest possible uncountable ordinal, then automatically PRI can be one projection skeleton, because you can take as index set just ordinals. And what else? Whenever you have a projection skeleton, then you can diminish the original index set gamma to gamma prime, so that this smaller guy is a PRI on X. Now, when I saw the concept definition of projection skeleton, then I asked myself, what does the enigmatic index set gamma look like? In PRI, the index set was consisted of from ordinals, but what about skeletons? And the first answer to this was, it came from the heavens of logic, elementary submodels, and so on and so on. Some of you are familiar with this, but some other not. So then still this was not satisfactory answer. And below I will show you that as gamma you can take some rather terrestrial objects, not those coming from logic. Because gamma can be a suitably chosen rich family. Wonderful. I will discuss this later, and now let me mention a few popular non-separable, few popular classes of non-separable Banach species. WCG, definition, immediately every separable space is such, and some less trivial examples are reflexive spaces are such, CK with K Eberlein, blah, blah, blah. Then Vašák. Vašák was a Czech mathematician 1 year younger than me and still alive, I hope. But after introducing the concept of Vašák spaces and proving something, he left mathematics. This pity. So Vašák means that you can find a set of irrational numbers and a upper semi-continuous compact valued from sigma prime onto X, and the topology on X is weak topology, and that's it. This is the definition. Our father, mathematical father, Professor Frolik, was familiar with this, and actually Vašák grew up from his atelier workshop of Professor Frolik. David Price was also roaming around. Next class, oh, by the way, every WCG is WCD. This was not known at the first moment, but this is true, and this is not difficult to prove. Next bigger class is a class of WLD spaces, and here is the definition. Some countability is behind. For instance, CK when K is Corson, and Corson is something bigger than Eberlein, and my K should be, in addition, have property M that every Borel measure on K should have a separable support. Yet a bigger class is due to Anatoly Plichko from Ukraine. If there is a linearly dense set, blah, 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 such that a norming property means that with help of set D, you can find an equivalent norm. And this class is pretty big. Andre Calenda found a big list of candidates. Capital L1 with any sigma additive measure. Yeah, Eberlein was here mu sigma finite. So this is sigma additive. Duals to C star algebras. People like C star algebras. Order continuous lattices. Some abelian groups are involved in this club, and so on. Now, some statements. How can we characterize spaces which are both Asplund and simultaneously WCG? So, The second property is very much like that from the characterization of Asplund property, but there are some extra moments. So here we have again that the assignment x star going to x star intersected to V is surjective in isometry, and moreover, these two innocent requirements. Yeah. And the third property, with help of skeletons. So Asplund property was also characterized by skeletons, if you remember. And the same is here, just the skeleton has some extra properties. That is that this family is also a projection skeleton. And the commutativity, if you like, you can add or you cannot. So this is optional proof, just for illustration. One implies two. Once X is Asplund, then there exists a nice, very specific rich family A consisting of rectangles, so that it has some properties from theorem 2. Now, once X is WCG, then using very elegant concept of Orihuela and Valdivia projection generators, they find another rich family, say W, so that blah, blah, blah. And now, as I said, the most important property of a rich family is that the intersection of them is again rich. So what will be the next step? The next step? Just this definition. I produce intersection of A and W, and this will be the rich family mentioned in property 2. And what about 2 implies 3? So, as you know, 3 speaks about skeleton. So first, we should say what is gamma. As I already mentioned, that frequently, or maybe always, gamma can be considered as a suitable rich family. So here we put gamma equal to AW from the second step, second assertion. And the order will be this one. And that's it. Then immediately, of course, using some things from algebra also, you can produce this statement. And what about 3 implies 1? So it needs a longer but not deep work via transfinite induction. So again, let me recall that for PRI, there was no chance to find characterization of Y and 3. So replace here projection skeleton by projection resolution of the identity. There is no chance for such a statement. So this is why projection skeletons are so useful and modern, and this makes a raison d'etre for projection skeletons. Now, using elementary submodels from logic, for non-experts, let me say just one thing, that those are things where somewhere behind there is famous Lowenhigh-Skolem theorem. In Prague, we have a group of some 5 people who are familiar with this stuff. I heard about it, but I am not an expert. And those who knows this modern technology, then it is quite helpful. But otherwise, to study it and to perform arguments, so Wieslav Kubis is one of those who had this technology, and he proved in his seminal paper, where the definition of projection skeleton was introduced, the following. Banach space is Prichko if and only if it admits a skeleton, which is moreover commutative, and everybody can guess what it means. So here is the definition. Such a statement. And I think one direction is rather easy, and the problem, what is rather difficult, is necessity. And later, Marek Cud and myself, we found an elementary argument without using logic instruments. Yeah. So, what else? Now, some other statement where projection skeletons can be found. Characterization of weakly compactly generated spaces. And here is the equivalent condition. The existence of very specific projection skeleton and commutativity, one commutativity, if you like, you can have it, which is moreover shrinking. And shrinkingness means, I will try to write down it on the blackboard. This is something like n x a is equal to p sub gamma n x. A shrinkingness means that if I have a sequence gamma 1, gamma 2, blah, 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 increasing, then I have such a quality where this embellishment by A means a topology of uniform convergence on the set A. So, for instance, if A is unit ball, then we have norm convergence, but here A is rather a slimmer object than the unit ball. So, using this pattern, paradigm, if you like, it is possible to find characterization of other bigger classes like weakly K-analytic Bashar spaces. Some people call it WCD. So this is Claudia Correa, Marek Cud, and Jacopo Somalia. Question of Wieslav to characterize Banach spaces which are simultaneously Asplund and one Prichko via a projection skeleton with some extra properties. To find these extra properties, he doesn't know. Have one more result. If you have a countable family of projection skeletons, then there exists one very specific skeleton called simple, and the simple means that the index set consists of the ranges for every gamma, and the skeleton should be isomorphic to a subskeleton of S sub I for every I. And the definition of subskeleton and what is isomorphic, you can think about it, nothing artificial, just natural way how to define such things. And unfortunately, I would say, some people say, great, the proof is done using elementary submodels from logic. So I would prefer, or I am curious if it is possible to find an elementary proof without logic, without Lowenheim-Skolem theorem somewhere behind. And now something from a different barrel, You know, I partially work in the so-called variation analysis. And in variation analysis, people focus on the following. If you have a mapping from X into Y, say F, the question is if this mapping sends a neighborhood of a fixed point into a neighborhood of the image. And such a phenomenon is called regularity, as Alexander Joffe, who is number one in this area, says so. Such a concept is called regularity. And here is the statement. First, so this is my set-valued mapping, capital F. Its double arrow means that points of X are sent into sets. Okay, and if you have two set subspaces Lm, then we can consider the following construction: intersection of graph. By the way, I do not distinguish between the mapping and its graph. This is not, some people do not like it, but if you go to books like Engelking or so, then it is acceptable. So I take the graph of F and I intersect it with this rectangle, and I denote such a restriction F sub Lm. And now the statement comes. Alexander Joffe, Julian Rewalski, and myself give me any complete metric X and any Y and any set valued F with the only extra property that it has closed graph. Then this enigmatic functor is something which assigns to the mapping F a number rec F dot dot. Later I will explain it. Such a factor is separable reducible, which means that, as you could expect, there is a rich family of rectangular form, so that for every fixed rectangle from R and for every X, Y from the graph of this restricted mapping, we have such a simple but deep equality. Regularity of the whole space is equal to the regularity of the restricted, I beg you, regularity of the whole mapping is equal to the regularity of the restricted mapping F sub Lm. And for those who wanted to know what is reg, here is the definition. So infimum of some case, and here we check such an inclusion with some quantifiers, and that's it. So, and a few words about the proof. The proof is complicated. We had to work not with just two different rich families, but countably many rich families. Fortunately, we could perform the intersection of them. And as regards this statement, here I would like to see opposite. We do have theorem 8 proved in elementary way. Is it possible, would somebody be enthusiastic enough to rewrite it using logic? And I would expect that the proof will be shorter. The point is, when using logic, that all the dirty work was done once forever in the proof of Lowenheim-Skolem theorem. It seems that this is all I wanted to say, and hopefully I attracted you to all the three concepts: separable reductions, which are 4 decades old, rich families, which are 20 years old, and Projection skeletons, modern substitute of Lindenstrauss PRI from 2009. Thank you very much for listening to my lecture.